Okay, I am recording. So, does anybody know what a harmonic oscillator is, or harmonic motion? Or can give us an example of a harmonic oscillator? You haven't seen harmonic oscillators in class? You probably didn't call it that. You probably called it a mass on a spring. Have you seen the mass on a spring in class? No?
Yeah, we have.
You have? In which chapter?
Harmonic motion, I think it was 7 or 8.
Okay.
I don't know, I stopped keeping track of the numbers.
What happens when you have a mass on a spring and you pull on the mass a certain distance, a certain length?
I think you're building tension, or like you're building its potential energy.
Yeah, that's true. You give it a potential energy, and then when you release it,
that potential energy is converted back and forth from kinetic back to potential, depending on what point it's at.
Right, and the mass keeps moving, right?
Yeah.
And oscillates and oscillates and oscillates, and the motion never stops. Okay, doesn't get interrupted, and continues forever. Okay. In an actual lab, of course, our experience shows us that it would come to a stop eventually, but that's because of the limitations that we have, right? Because we don't have a frictionless surface, okay? And there's also air resistance, and there's also the friction of the spring itself. That's what causes all of those effects are what cause the mass to stop oscillating eventually and come to a stop, okay, at its equilibrium position, okay? But without that, if you were able to remove the friction, go to outer space, for example, or to a lab where there's no air, okay, you would see the spring move forever. It would never stop. So this is an ideal case of simple harmonic motion. Okay, can you describe it more? Because we're going to need all the properties of this process. For example, how does the speed change?
I think this speed.
Where is it highest and where is it lowest?
The speed should be highest at the point farthest from the
in the equilibrium position?
Yeah.
Of the mass in the spring? Is that correct?
Or is that the opposite? Because
you see, how about the velocity? The way to think about it is to think about it in terms of velocity, okay? The velocity, you see, if let's say you are pulling it to the right? If you pull it to the right, it's going to move to the left, okay? It's going to move to the left until it reaches the end point on the left. But the velocity vector during that motion will always be pointing to the left. When it reaches the left end point, the velocity vector is going to switch and point to the right, okay? But you see, because the motion is continuous, okay, the velocity is not going to change all of a sudden from left to right? It's not going to happen like that. It's going to change in a continuous way, slowly, and then point in the opposite direction. Instead of pointing to the left, it will point to the right. Since it's one-dimensional motion, the vector part of the velocity, the direction of the velocity vector can be described by the sign of its component, right? So it's negative as it moves to the left. Once it reaches the end point and it starts moving to the right, then the velocity component becomes positive. But then how do you go from negative to positive? You have to go through zero. So it has to be zero at the left end point. Okay? And same thing for the right end point. It has to be zero. So that's why the velocity vector is zero there. Okay?
Okay, thank you.
Another thing. How about the force? What is the equation for the force of the mass on a spring? Oh, it's called the Hooke's law. What's Hooke's law?
The force in the spring is equal to the amount of compression times
that's yes. Okay.
Times a constant.
Yes. Let's call it x. Okay, so it depends on the position of the spring. X. Let's call it x. Okay. Let's make x equal 0, the equilibrium position. Okay. So when the mass is at rest. Okay. So at that time x is 0. Now, as the position from equilibrium, that's what we are going to call x. And then, as you said, you have to multiply that by a constant. And that constant is the spring constant, okay, which is everywhere called k. In all books, it's called k. Okay, that's the spring constant. And there's also a minus sign so that we make sure that that the direction of the force is correct. Now, the force changes during the motion of the mass. Where is the force highest and where is it lowest? I mean, this introduction is really going to help you a lot for your lab, because I've read the questions and many of them will appear. So the answers you give will help you answer those questions. So where is the force the highest and where is it lowest?
Would the force be the highest at the equilibrium point and then 0 at the endpoints, or lowest at the endpoints?
Okay, let's define. So we define the origin of our coordinate system, one-dimensional coordinate system, as being the equilibrium position of the spring, right?
Okay. Yes.
So, and then you just said that the force is minus kx.
Mm-hmm.
If it's minus kx, plus another way of thinking about it, okay? Another way of thinking about it, you've all played with springs when you were children. Yeah. I have. I'm sure you have, right? When you pull on a spring, so the mass becomes your hand, basically, okay? When you pull on a spring, a little bit, okay?
The force is highest at its endpoint.
It's highest, yeah. When you pull a little bit, the spring doesn't pull back on you much. But when you pull a lot, right, it pulls back on you harder, right? So therefore, this force has to be highest at the endpoint, okay? And where is it 0?
At the midpoint or the equilibrium.
Right, the equilibrium. Okay. Another thing, force equals what's Newton's second law? Mass times acceleration, right? Mm-hmm. Since force is mass times acceleration and mass is a number, right? The direction of the force must always be the direction of the acceleration, right? And then, and also, the magnitude of the force is proportional to the magnitude of the acceleration, right? And the proportionality constant, of course, is the mass, right? So if the force is big, you have to expect the acceleration to be big too. And if the force is small, you have to expect the acceleration to be small. What if the force is 0? What is the acceleration in that case?
Should be 0, right?
Also be 0, right? So if they ask you what happens to the acceleration in these questions, right? Maybe it will be easier for you to think in terms of the force, because you have an equation for the force. It's minus kx, and with minus kx, you know, if you know exactly what position the spring is in at all times, you know its force. And if you know its force, you know its acceleration because you know its mass. Okay, so the relationship between all those variables will become important in this lab. All right, so the first page basically tells you a little bit what those all these variables represent, and gives you a few formulas that you will need in your calculations. Okay, it tells you that the period is the reciprocal of the frequency. We've dealt with periods before when we studied circular motion. Okay, when we studied circular motion, and so we know what a period is by definition. Period is the time it takes for one cycle to happen. Okay, that's what the period is by definition, one cycle. So for us, one cycle will mean, so if you start from the right, so if you pull on the mass to the right and you release it, one cycle will mean it goes all the way to the left endpoint and then comes back to the right endpoint. Okay, so it has to come back to the right endpoint, right? Not the time between, yeah, you can tell, say, 2 swings, I guess. Yeah, so the time to go one way and come back. Okay, that's what our period will be. Then you have the angular speed, which is 2 pi over the period. And then you have a formula for the acceleration. All these formulas will become important. And you have a formula for the potential energy, which is 1/2 kx squared. And one for the angular speed in terms of the spring constant and the mass. That's the square root of k over n. Okay. Okay, I think this is what we will need in this lab. And this should be enough. So let me start. We are told to, I'm on page 2 now. We are told to click on intro, the intro window. And there's a whole bunch of springs. So we are going to use spring 1 in this experiment. Okay. Select 3 as the spring constant. We are already at 3. Okay. For spring 1. So we use the gravity of Earth. So we have to check the box's natural length and equilibrium position. Natural length, equilibrium position. Select the ruler and the stopwatch. Now I have to warn you, this ruler, even though these tick marks seem to be millimeters, they are actually centimeters. Okay, so 10 does not mean 10 millimeters. It means 10 centimeters. Okay, it's a bit weird, but that's the way it is. Okay, yeah, 10 centimeters. So yeah, so the length of this ruler is an entire meter. So select 250 grams for your mass and attach it to spring 1. So that's what I'm going to do. So you see, there are two different things. We have the equilibrium position of the spring, and then once I attach the mass to the spring, the equilibrium position is going to change because of gravity. Okay? In outer space, nothing would change. But because of gravity, it's going to become lower. See? It goes down and reaches, sorry, this green line. Okay, so that's the new equilibrium position. That's the equilibrium position that we are going to talk about. When I say equilibrium position, I do not mean the blue dashed line. I mean the green one here, right? That's the equilibrium position of the mass and spring system. Okay, this blue one is completely meaningless. It's not going to help.
You can turn off the blue one.
We can turn it off.
Yeah, if you uncheck it at the top, it gets rid of it.
Yeah, yeah. But I want to keep it there because we are told to do so, and yeah, I want to keep it there. But in our lab, when I say equilibrium position, I will mean that of the mass spring system. Okay, not where the spring is in equilibrium, but with the mass attached to it. Okay, so what else are we told today? So somebody else just came in. Okay. Right. Yes. I think that's it. I think there's nobody in the waiting room. All right, so select 250 gram mass and attach it to the spring. Press the red. Remove this because it's oscillating a little bit. Okay. Okay. So press the red stop button at the side of the spring one to stop the oscillation. So the oscillations have stopped. Okay. Measure and record the value for extension of spring one with 250 gram mass attached. Okay. So if I take my ruler and put it here, the blue line, and compare with the green line, what are you guys reading as the extension? Of spring
40.
40, 41, right? 40, yeah. 41, 15, 41. Okay.
Yeah, 41.
Centimeters, right? It's gotta be centimeters, not millimeters. All right. Now we are asked to pull the mass downward away from its equilibrium position for an extension between 10 and 20 centimeters and release to begin oscillations. Okay. So let's say here, so 10, 20, between 10 and 20. So maybe 15. Okay, I'm okay. So remember, okay, let me stop this. Let me stop this. Okay. So now you have to know. So the equilibrium position is the position of the hook. You see the hook where it is? That's where the equilibrium position is. In another part of the lab, unfortunately, they would change their convention for the equilibrium position. I think they'll put it at the center of the mass. Okay, but it doesn't really matter, right? That doesn't really change the physics. Okay. So, but for us, for this first part, this introduction, the equilibrium position is at the level of the hook. So if I want to move it 15 centimeters, it's going to be about here. It doesn't have to be 15. It can be anywhere between 10 and 20. Okay. And then it starts oscillating when I release it. Okay. And this should never stop. Okay. If there is no air resistance, no friction. Okay. Which we call damping. We call that damping. Okay. But there is none here. So it has to move forever. Now, so what are we taught to do? Use okay, so use the stopwatch to time for 10 oscillations. Do 2 time trials and get an average for these 2 runs. Okay, so I'm gonna wait. You have to time this very well. I'm gonna wait until it reaches maybe the bottom. Okay, and then I'm gonna press play to start my stopwatch, and then I start counting. But to count, I have to count each time it reaches the bottom end point, not the bottom and the top end points, not both of them, just the bottom end point, so that I have a complete cycle. Okay, so I have to count up to 10. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Nice. Okay, so 12.79 seconds. Can you please write that down somewhere? Because we will need in our calculations, so we can go together. You can help do the calculations. But I had a piece of paper. Yes, I do have a piece of paper. I need a pencil. So the time for 10 oscillations or 10 cycles is time for 10 cycles. I prefer the word cycle. Instead of oscillation, 10 cycles is 12.79 seconds. Okay. So now I should do this twice and then take an average, and that's what you're going to do. Okay. But me, I'm going to stop here. I'm just going to do it once. Now you need to determine the periodic time, the period t. I'm on part A. So how do I get the period t? Somebody has any idea of how we can get the period once we have found the time for 10? How do we get a period?
So let me pick 1 divided by frequency.
Excuse me? Can you repeat?
So isn't period equal to 1 divided by the frequency?
But do we know? We don't know the frequency, do we?
Oh yeah.
Using the data that we have.
I don't know.
Oh, I didn't notice this. We can actually slow down the motion so that it becomes easier for you to count. You see there's a button here. But this is a little bit slow, yeah?
It's a little too slow.
Too slow. But this will come in handy in the next part of the lab. Yeah, it will become very useful in the next part. Okay, I didn't know that. Okay, now that's good. So, so how do we get the period? Uh-oh. Okay, let me pick somebody at random. Adalio Casio. Oh, no, he's not here. Christopher Ortega. Christopher?
I'm still a bit confused on how to get the period.
Okay, so what is the period by definition? Okay,
It's like 1 over frequency, I think.
I think the period is the amount. Fuck, it's
The number of like. Sorry, you could go. Sorry.
I was gonna guess. So if you know, go ahead.
Isn't it like the number of like revolutions or cycles like over a time period?
Yeah, that's what I was gonna say. Like we know we have a time we're given, and we know how many cycles it does in that amount of time.
Yeah.
So we should be able to calculate something from that. I don't know what we're gonna call that.
Let me define the period once more. The period definition, okay, is the time it takes for one cycle to occur. Like the period. Earth's orbital period, or Earth's orbital period is 1 year because it takes Earth exactly 1 year to go around the sun. Earth's rotational period is 24 hours because it takes 24 hours for Earth to rotate once around its axis. Okay, just one cycle. Okay, so what would the period be for this case?
So would it be 10 divided by 12.79 or?
Why?
Or like the other way around?
Yeah. But you see, the units don't. If you do it like that, the units won't be correct. But what are the units of period? Because we said time it takes to go to one cycle, so time is in seconds, of course. So something in the chat. Yes, Tavares, Harold. Yes, that's correct. 12.79 divided by 10. So if you take 10 divided by 12.79, then the units are not correct because seconds will be in the denominator. Okay. So it's 12.79 divided by 10. Okay. So the time it takes for 10 cycles to occur divided by the number of cycles, this gives you the time needed for just one cycle to take place. And that's 1.2779 seconds. That's 12.79 divided by 10. Okay, so that's our period. You see, this is very much like circular motion. Okay, and in fact, the two processes have a lot in common. Okay, and we use the same variables for them, and their solutions are the same, and so on and so forth. Okay, so determine the spring constant using two different methods. Okay, they are giving us the force divided by the position. We can use that to get the spring constant. And secondly, we can use the other formula, 4m pi squared over t squared. How can we get the force? So position, so we are a little bit faster and you have time also to practice. Let me help you a bit. For position, so f over x, position x, because it's a little bit hard to know the position everywhere. Okay, in the trajectory of the spring of the mass. Okay, I will take the endpoint. Okay, so the original extension, which was 41 centimeters. So when the spring is at was it 41? No. It's 20 centimeters. What did I choose? I think I chose 15, right? So x equals 15 centimeters. Okay, so that's the yes, 15 centimeters. That's where the hook was before I released it. Okay, 15 centimeters below its equilibrium point. Okay, so what I can do is, so that's x. X is going to be 15 centimeters because that's the only position that I know for sure. Now, what is the force there? Well, I can't use minus f plus minus kx because I don't know what k is. That's what I want to solve for. And I don't know what, I know x, but I don't know what k is. So what else? How else can I get the force? Mass times acceleration. I don't have any value for the acceleration. Or well, actually, we do have a value for the acceleration, don't we? Okay. These are formula on the previous page. So if I use that formula, okay, and plug in the x, which is 15 centimeters, plug in omega. What's omega? That's the angular speed, but it's related to the period, which we have just calculated, and we found it to be 1.279 seconds. Omega is 2 pi divided by that, by the period. I can plug all of that there and get the acceleration. Multiply that by the mass, 250 grams, but then it will have to be in SI units, have to convert to SI units. So that's a quarter of a kilogram. I should get my acceleration. Okay, my force, sorry, because I already have the acceleration through the angular speed. So I get the force, and if I take that force and divide by 15, that should give me my spring constant. You understand how I get the spring constant in the first case? Should we do it together? Can somebody do that? So on the first page, you have a formula for the acceleration. Omega squared x. But we have to find omega first. Omega is 2 pi over the period. So let me do that. 2 times pi divided by the period, which is 1.279, and I get omega, which is 4.9. We write that down. Are you all getting the same value? Because 4.912, let's say 6. Okay, and everything is in SI units because the period was in seconds. Okay, but then I have to square this.
Okay, I also got 4.9.
Right, that's good. That's good. Keep maybe 4 decimal places. Okay, but then we have to square this. I just squared it. So omega squared, and then multiply that by x, which was 15 times 15. Okay, and I get my acceleration. So acceleration is 362. That's what I found as my acceleration. Okay, 362. But then I have to multiply with the mass, which is 1/4. Okay, 250 grams. The 1/4 of a kilogram, because I have to convert that to kilograms, SI units. So multiply that by a 4. So that gives me the force, and then which I get as 90 0.5 Newton, and I divide that by the position x according to the formula, which was 15 divided by 15, and I'm finding 6. Okay, so spring constant K equals 6.03. And what are the units of spring constant? The units of the spring constant. But you see, from the formula, Hooke's law, force equals spring constant times the displacement. To get K, you can divide both sides by the displacement x, and you get K equals F over x. F is in Newton, the displacement is in meters. Therefore, the spring constant must have units of newtons per meter. Okay, so that's what I'm finding using part I. If you use part 2, double I, well, they gave you the formulas, so you can just plug in. You know the period, you know the mass, so you should get K easily. And you have to find the same value as we found in part A. Okay. Well, part C and D, you have to do it yourselves at home. But using this method, the one that I just described, there is no difference, because the formula from part A, from part 1, gets you or leads you to the formula in part 2 right away. Okay, so that will all depend on how you will compute the force. You don't have to do it the way I did it. Okay, but, that's what I chose to do, because I thought it was simpler. Okay, now we have to determine the mass of the largest unknown mass. Okay, all right, so let me remove the 250 gram mass. I have to stop the motion first. Remove. And you notice that the oscillations kept happening uninterrupted, and they did not die down, right? Because we don't have any damping. Now we need to find the mass of the large mass. So I attach it to the spring. Okay. And then I have to move it a certain distance. Let's say it doesn't have to be the same 15 as before. Okay, we stop this. Can move it maybe 8. This looks like an 18. I release it and it starts oscillating. Okay. Now I need to find its mass. How would I do that? Any idea? How will I find the mass? Let me pick somebody at random. Stanislav. Stanislav, are you here? Not here. Okay. Ravika Singh. Brevikasing. Harold, how would you find the
Yes.
mass? How would you find the mass? Any idea?
On how to find the mass.
Yeah.
Are we using one of Newton's laws?
You can use Newton, second law. So you would have to find the force and divide that by the acceleration. But the formula for the acceleration does not involve the mass. So you would have to find the period, find the acceleration, but then you need to find the force. How would you find the force though?
Right.
You can find it. So I started at 18. X equals 18 centimeters. Is that enough to get the force?
Well, don't you still need acceleration?
Yeah. Well, no. The acceleration that we just talked about, we can use it to find the mass eventually, okay, in the last step of the calculation. But we thought we first have to find the force. And since we have the initial position of the spring of the mass, okay, if you multiply that by the spring constant, Hooke's law is minus kx, that would give us the force. Now the question is, do we have a spring constant? And the answer is yes, because we just calculated it. The spring constant is not going to change because you have a bigger mass or a smaller mass. So it's the same for all masses. That's why it's called a constant. And we found it to be 6.03. Okay, so that will give you the force. And you divide by that acceleration, that will give you the mass. So that's one way. That's not how I did it, but that's definitely a way that would work. Okay. Now the vectors, part 2 of the lab. At the base of the screen, select vectors. Okay, select displacement. Mass equilibrium. Velocity. Acceleration. Gravity and spring. When we use Earth's gravity. We need to attach a 250 gram mass and observe the vectors during the oscillation. Okay, 250 here. Okay. Whoa. So as I told you, you see they've changed the equilibrium position, the convention, instead of being at the hook. No, it's still there actually. It's still there. Okay. So, okay, I see what they did. So blue is the velocity of the spring. So let me start the motion. Let me pull on this. And it starts oscillating. And you see that the vectors change. Okay? Now the first question is, at which point is velocity minimum or zero? I think that's when I should slow down now. So at which point is velocity minimum or zero? Velocity is the blue arrow, you see that? Oh no, it's the green one. Sorry about that. It's the green one. The velocity is the green one. So when is it minimum or zero?
At the start and at the end.
Okay, but I don't know what start and end mean.
Rather just like at the top and at the very bottom.
Yes. Everybody sees that? At the very top and at the very bottom, the velocity vector is zero. Okay? Because of the way I explained it earlier at the beginning, right? It has to change sign, you see, because it has to change direction. Okay, and it's continuous, so it has to go through zero in going from minus to plus or from plus to minus. At which point is velocity maximum? Maximum means the vector is the longest. When is it maximum?
It's like around that middle line there.
Okay. Which point is acceleration zero? The acceleration is the yellow one. Maybe I should remove the spring velocity because this is confusing us. Well, but we will need the. No, these are forces. These are forces. Sorry about that. So, acceleration.
Is it zero like in the middle?
So equilibrium position.
Yeah, equilibrium.
That's true. That's true. That's true. Equilibrium position. Now that's the acceleration. At which point is acceleration maximum? Maximum in length. That's what we mean. Okay, that's when we say acceleration here, we mean the magnitude. So that's the length of the yellow vector. So when is it maximum?
At the top and bottom again.
Right. Top and bottom. Endpoints. Yeah. So you will have to slow down the motion for this part of the problem because otherwise it's going to be too hard to see. So if I press on normal, you see at the bottom right of the screen. If I press normal, it's really hard to see how these vectors are changing. When I click on slow, it's much easier. Is gravity ever zero? Gravity is red. Press on it. What's the answer to that?
No.
No, it's not ever zero. Okay. Now, it's not the zero. Is spring force ever zero? Spring is the blue. Let me remove the gravity so you don't get confused. It's the blue arrow. Is spring force ever zero? Yeah, and the answer is yes, right at the very top. Okay. Now, now the next question is, what happens when the spring constant is increased? Well, we can increase the spring constant easily here. Okay. Okay, let me I have a normal motion now. Normal. We stop it. Increase the spring constant, make it large. And then start all over and see what happens. So you have to describe what you see. Okay, you have to describe what you see. I'll make it smaller. See, there's a difference. I'll make it larger. See, there is a change. What happens when gravity is changed to that of the moon, of the planet Jupiter, and so on? So you can change that here and describe what you see. Jupiter, for example, you see what happens. Okay. All right. Determine the value for gravity on planet X. Okay. You can do that using the formulas that we have. Now, part 3. Are there any questions before we start part 3 live? Okay, part 3. Check boxes at the top right corner for natural length and equilibrium position. Natural length, yes, mass equilibrium. Select rule and stopwatch for linear and time measure respectively. So set spring constant and damping such that the spring constant is greater than the damping. Okay, so now we will have damping. So we put all of this in water, for example, or in honey or in whatever. But we want the spring constant to be bigger. Okay. Select non-100 gram mass and attach it to the spring. Okay. Supposed to be 100 because I used it earlier. So now I can change the mass. Okay. If it were 100, this is what could happen. Okay. 100. But then we are told to adjust mass measure to value greater than 200 grams. So I have to increase it to 277, for example. Okay. Now the mass page. Stop. You have to stop the oscillations. Okay. The extension, you measure the extension. Okay. With the ruler, here to here. It looks like, what does it look like to you? The extension. So again, you have to go from the equilibrium position of the spring to the equilibrium position of the mass, which is at the hook. What's the extension or the new equilibrium position of the spring? Or somebody, it's in the chat room, somebody answered the question, I believe. And it's finding. I can't, because I'm sharing, I can't see your answers. I can see, can somebody say it aloud?
48.
48, you said?
Yeah.
Yeah, about 48, 46. Yeah. Well, but you have to be is the hook. You see the hook? That's what you have to look at.
Right. 47.
Yeah, about that amount. Okay, so where the hook is. And the reason is, you see, if I remove the mass, you see this is where the spring was, okay? At the very tip. That's where the blue dashed line is. If I touch the match to it, goes down, oops, and then I stop the motion. You see, this is the new position of the hook. And we have to measure the distance between these two positions. So it's about 47, 46, 48. Yeah. Now, use the stopwatch to time for 10 oscillations. do 2 time trials and get average of these 2 runs. Okay, we want to find the period once more. I've shown you how to do it, so now you can do it. Okay, you have to pull on the mass a little bit, but record the value of the initial position. Okay, initial position will be, okay, if I do that, okay, the initial position will be the difference between, so let me put my ruler, it's going to be 0 at the hook, okay, and then I observe the hook. Where is it going to stop? I can stop it at 20. Wherever the hook is, that's where my initial position will be. Okay, so 20. Did I do it right? Yeah. So, okay, here, 20. 20, and then I release it. But I have to write down the measure first. Write down 20 on my sheet of paper, and then I release it, and it starts oscillating. Okay, and then you have to determine the periodic time. Okay, but be careful now, because now we have damping. Okay, so the oscillations are going to die down. Okay, so so maybe you can slow down the motion and compute the time it takes for just 1 cycle. 20, so everything is slowed down. And here's my stopwatch, and I measure. This can be done until it comes back. But then there is damping, so it's not going to come back to the original position. Okay. Calculate the spring constants. So in order to do this, okay, you have to remove damping. Okay, remove damping. So none. In order to find the period, because this wouldn't make any sense with damping. Okay, so let me stop the motion and start again. Okay, it's slowed down. So let me do a normal oscillation. So you see that they don't die down anymore. The oscillations do not die down because I've removed the damping. So that's what you should do in order to find the period and the spring constant. Now, determine the energy of the spring at the top of the oscillations. How would you do that? The energy of the spring at the top of the oscillations. So let me remind you that we have the initial position, which was, I think, 30 centimeters. 30.
I think you should use the formula.
Which one?
1/2 kx squared.
Correct. That's correct. 1/2 kx squared. That's what you should do. Okay, so that's going to be the energy of the spring. And the energy of the spring at the equilibrium position, that's what should that be? At the equilibrium position. That's where x is 0. So you would expect it to be 0. Energy is 0. Okay. Now we need to determine the energy of the spring at the lowest point in oscillation. The energy, determine the total energy of the system. Okay. We have to think a little bit to do that, but it's not hard. Unless you have an idea, and then you can let everybody know how to determine the total energy of the system. How would you do that? Total. So on part H, determine the total energy of the system. How would you find that out? What do we mean by total energy of the system?
Isn't it just the maximum amount of energy it has at
And
like any point?
Okay, the energy is conserved, so this energy is not going to change. At any point, it's going to be the same. But how do you compute it? That's the spring, the energy in the spring, plus the energy of the kinetic energy, and we have formulas for both. Okay. The problem is that the kinetic energy is going to require the speed, because you have speed squared, 1/2 mv squared. But how are you going to get the speed? That's the problem. That's the problem. You're not going to get the speed. However, let me give you a clue. If I click on the velocity vector and I slow everything down, you see that's the thick green one. It's the thick, not the thin one is the displacement from the equilibrium position of the spring, not the mass spring system. If I slow everything down, look at the way the velocity of the mass changes. Okay? Because it's that velocity that enters the formula 1/2 mv squared in the kinetic energy of the mass. Okay? You see how it changes. Still not helping. However, see that at the top, at the very top, and at the very bottom, the velocity is 0, right? 0. Very top is 0. Very bottom, the velocity is 0. That's exactly what we discussed at the beginning. If it is 0, the velocity is 0, that means the kinetic energy is 0. But since energy doesn't change, this is an isolated system. There are no external forces. There's no heat exchanges. It's isolated. Therefore, the energy is conserved. And since it's conserved, it is the same at the top as it is everywhere else. So can that help you find the total energy of the system? Since we said it's the total of the spring energy and the kinetic energy, all there is at the top is just the spring energy. So this the energy of the spring at the top or at the bottom should give you the total energy, since the kinetic energy of the mass is 0 there. Okay, so that's how I would do that. Okay, and to find the total energy, I mean the spring energy, all you need is k times x squared. But finding the spring constant, we found that in part D, using the period, which we found in part C, and then the displacements, that's what we recorded at the very beginning. That's the initial displacement. Okay. That's all there is. I mean, there's also part I, but that's you should be able to show that very easily. All right. Are there any questions? No questions. I think you can start on your lab. Start working on it. We have 20 minutes, but because the lab is due in 2 weeks, you can keep working on it next time.